So I guess my talk sort of starts off where Andreas's talk ends. So he told us about all these amazing things about that WebAssembly has. And so this talk is going to be sort of maybe a little bit, like a spoiled child saying, well, okay, but we want more. And it's a bit of an ad for a research program around WebAssembly in Aarhus. So maybe the starting point is, why is WebAssembly successful? And WebAssembly is successful for a whole bunch of reasons. It's portable, it's got high performance implementations, it has a cool logo, many other things. But one aspect that I'm going to talk about that I find is particularly important is safety, which is, I don't remember who it was, maybe Conrad, you remember, but it was, I think, a WebAssembly workshop where someone described it as a sprinkling of fairy dust that adopters would sort of be lured by and go to WebAssembly and start using it. And this idea is that safety sort of makes adopters and users sort of feel comfortable about the language. But what does it concretely buy them? And so the question is, what is safety, and in particular, what is safety in the context of WebAssembly? Maybe the first thing to answer is, what isn't safety? Safety is not a single thing. It's not clear to me what a master definition would be, even if there is one at all. And so it's an open-ended process. We have to find out what it means. I think it also depends on the language. Different languages will have different definitions of safety, so it's not like we can take another one for WebAssembly. And even within WebAssembly, I think different users have sort of different concerns or different threat models. So in particular, Chrome assumes that type checking goes wrong because it's too complicated. And as Andreas described, WebAssembly changes over time anyway, and so this changes what the definition of safety is, and I can give you a concrete example later. So why should we even care about safety? Well, there's this famous paper, Everything Old is New Again, where they show that, in a sense, safety is easy to misunderstand, and people have misunderstood it in the context of WebAssembly, and sort of this has had consequences where people thought that the language gave them something that it didn't give them. And so my goal, my interest is to clarify and state what this sort of fuzzy fairy dust is, and try to show maybe that it's real, that you do get some concrete guarantees. So what is safety, or maybe what are aspects of safety? So one that Andreas described, and one that is actually in the standard, right, is type safety. And this is, as Andreas said, it's a very old notion, and Conrad gave us sort of the version of that, or formalized the version of that we have for WebAssembly. And so this gives us like a very concrete aspect of safety. But it's only one aspect. I think there's other aspects. One of them that I think, if I remember correctly, the standard kind of hints at is some form of control flow integrity, that there's some separation between code and data. And of course, everyone sort of informally knows that about WebAssembly. You look at the language definition, and you kind of see, okay, the two are separate. But it's a very sort of fundamental thing when you're thinking, okay, I want to adopt WebAssembly as a technology. This can really be a sort of an important property that makes you think, okay, this is a good fit for what I want. This is really an important guarantee for me. But even within sort of control flow integrity, there's different aspects. There's this pure sort of Harvard architecture, code and data are separate, but there's also the aspect of well-bracketed control flow. So if you have calls to functions, then they behave in a well-bracketed way. If you call f, then G should return before f can return, right? You don't have f, G, F, G. That's not a sequence of things you can observe. But this changes with stack switching, right? This completely becomes possible, this kind of sort of subversion of control flow. So it's a thing that has it's a part of safety that has changed throughout the still relatively short history of WebAssembly. And you might imagine that people who sort of designed their threat model, designed their sort of idea of why WebAssembly is the right thing for them, they might be surprised if suddenly there's a new language feature that kind of breaks this. And then there's lots of other aspects of safety. So for example, everything to do with side channels and all the side channel based attacks. I think WebAssembly sort of doesn't promise much in that direction, although there is this work by Conrad and others on sort of constant time versions of WebAssembly that do guarantee you a bit more. And what I'll focus on sort of mostly as an example here is isolation. Right, so here the idea is sort of isolation of parts of your programs between each other, and there's many aspects to that, and I'll return to that. But the idea is, as I've kind of sketched, that between all of these different aspects of safety, some of them, like the first one, are very clearly and explicitly stated in an appendix to the standard, and some other are sort of much more fuzzy. Fuzzy both in what they mean and in sort of how precisely they're stated and described, and how authoritatively they're described. So to zoom in on isolation, well, isolation itself has several aspects. And one of them is sort of what I'll call external isolation, which is sort of the umbrella of sandboxing, right? So it's an isolation between the program and the outside. And if we zoom in more specifically, something like, well, the program doesn't access memory outside of its linear memory, or doesn't try to access things outside of its linear memory. And this is at the same time a property of the language. You know, WebAssembly sort of has checks at every step of the execution, but it's also a little bit a property of the runtime. You know, you could perfectly imagine having an implementation of C that does exactly the same thing. It's not what the language requires, but you can do it. And there's another aspect of what I'll call external isolation, which is that the process doesn't manage to access memory outside of its process, rather than it doesn't try. And this is, well, it's not so clear. Is it a property of language, or is it a property of, you know, the operating system and its process isolation? So in a sense, it's not really, you know, in the context of WebAssembly, whether the program is sandboxed is not even clear that it is a property of WebAssembly, even though, you know, people associate very much WebAssembly with sandboxing. So I think it's worth bearing these things in mind. Andres is making very funny faces. I don't know if that's success or failure.
Yeah, because I mean, the semantics tells you what is happening with every possible execution, and none of that involves any sort of dependence on outside state, right? So how
well, yes, but it assumes that your runtime is implemented correctly, and in a sense,
well, sure, but I mean, if your implementation isn't correct, then none of the guarantees of the language hold anyway.
You could also have a correct runtime that just arbitrarily mutates the external state on every step of WebAssembly. You preserve the WebAssembly semantics.
Whenever you do an add, it just writes to a random location in memory outside of your WebAssembly program. It's a bit contrived, I agree.
But that would not be observable from within WebAssembly, right?
Yes, but I think...
Well, except through host calls.
Yeah. Okay.
Except through host calls.
But then it's sort of a semantics of the host call.
Yes.
Yes.
That's the point.
Yeah.
Which I think, my point is, you really have to think about these things. It's really like, sort of, it's easy to sort of think in a very naive way and zoom in, oh, you know, there are these checks and therefore it's all fine, but you actually need to think about, you know, maybe there's this sort of weird, not quite side channel, but a secondary channel that sort of loops back through host calls. But I move away from external isolation and zoom in on internal isolation. And this is really isolation between parts of the program. So sometimes people call that local state encapsulation, or there's a bunch of other terms. And the idea informally is that things that should be separate actually stay separate. So for example, this is things like locals can't be accessed outside of their function, which is very different from, let's say, languages like C. Right, so you know, this might be, again, not a very strong reason to adopt WebAssembly, but it might sort of encourage you a little bit. Like, you know, it has this kind of sensible structure. Another property that's maybe more important for sort of actual use cases of WebAssembly is that one module's non-exported memory can't be accessed from other modules. Right? And these are really purely properties of the language, right? This is a thing that, you know, when you're reasoning completely about your program, not the interaction with the outside and other things, it's really, you're defending part of your code against other parts of your code. And then there's many other types of isolation, but I want to zoom in on this one here. And the reason is that this is really to do with language properties, all right? So language properties I think are important because users implicitly, also a little bit explicitly, rely on them when they program. And also because they're a very important use case of WebAssembly. As I said, I guess sort of underlying many of the use cases of WebAssembly, let's say in edge computing or things like that, there's this idea that if you link with another module, or in WebAssembly terms, if you combine with another module, like if you instantiate two modules next to each other, then it's going to be safe. Like there's nothing that the other module can do that isn't explicitly allowed by a very well-defined and clearly delimited interface. So in a sense, if you link, or if you instantiate together with a sort of evil module, the worst thing it can do is trap. It's not going to corrupt your own internal things. And in a sense, WebAssembly makes this sort of possible and easier. And with the context of WebAssembly, you can really define what it means to be safe. And so there's this term, the universal contract, that has been introduced by the people cited at the bottom in the context of instruction set architectures. But the idea is that it captures a property that's respected by sort of arbitrary code in your language. Right? In WebAssembly, importantly, is any well-typed code, because instantiation will sort of kill any code that is not well-typed. Right? And so this universal contract, it gives you a guarantee about no matter what the rest of your program does, I know that my part of the program will always have these things that it continues doing well. So for example, if it has a non-exported memory, then it remains the only one with access to it. Right? And it's related to things that people like Wadler have called three theorems. It's the same idea in a sense. And so here is the point where I'm going to say, well, all the things that Andres described or offered us, they're nice, but I think we should have more. I think that the language standard, in a sense, should declare upfront some of the language guarantees of these universal contracts so that users and adopters know what they're buying. I mean, there's already, we're already on the way, right? I don't think there are that many languages that include a stated type soundness in the standard itself. But I think we can, and I think we should do more. So really the plan, and this is not just a plan for me, but I think it should be a plan for the community, is to identify these properties, state them, formalize them, and this is where it becomes maybe a bit hairy, prove them, and then make them part of the standard. And I think the idea then is that if you have a proposal that you want to extend the WebAssembly standard, then you should show not only not make implementations, but not just define new rules, but show that when you added these new rules, you don't break old properties that people expect of the language, or if you break them, explain, so give a good reason why you break them, and maybe give a fixed version. And I guess the stack switching example, it's a case where sort of along the history of the language, you have this, like the naive version of the property was broken. And this might, I'm not saying it actually happened to people, but it sort of gives a flavor of the kind of ways you might be sort of backstabbed by an evolution of the language if you don't have these very upfront stated properties. So in a sense, what I want to do is sort of a call for help, because I think there's lots of these language properties, and lots of people, different people have different requirements, different expectations about what safety is. And me sitting in my office, I can't really figure out all of them, let alone figure out which ones are important. I think we should have sort of as a community a discussion about these things to identify what are the universal contracts that people actually rely on in practice. And this is really, this is the main statement of my talk. And then the rest, I'll quickly describe a sort of case study of how we've tried to do that for one specific flavor of safety and why it becomes a little bit complicated. And so why maybe this very lofty aim, there's already speed bumps on the way. So zooming in on local state encapsulation, there is this expectation of sort of coarse-grained encapsulation, a coarse-grained isolation at the level of the modules in WebAssembly. Right? So if you state it in a sort of very rough way, one module's non-exported memory can't be accessed from other modules. That's, informally, it's a pretty good thing. I don't know whether the standard actually states that. In a sense, I think in the standard it's an emergent property. It's sort of like an accidental property of instantiation that it actually guarantees that. Well, it's not. I mean, it's not accidental in the sense that clearly it was written by humans with a purpose. But if you look at the document, it's an emergent property of the individual rules.
We actually discussed this, right? I would love to have some formulation of this statement, but like, how do you formalize that exactly? Like, I haven't seen any good solution to that.
Like this.
Involve 20 symbols. Okay?
I think 20, as you will see on the next slide, is a bit of an understatement. So I think, but I still think it's, even if the end might not be the most pleasant thing, I think the journey is still important and some of the milestones are important. So you can try to refine it by saying, well, one module's non-exported memory can only be accessed sort of through that module. So other modules can access it if they find a function from the module that sort of allows them to mutate that memory, and then it's only according to that function, in a sense, right? So, and then if you try to make that more precise, then it turns out to be a little bit more thorny, which is, I guess, the whole thing with contracts and ferries ending poorly. So if you try to make that precise, or at least to make a version of that precise, it kind of looks like that on the right here. So this is, I think, excerpted from Einer's thesis. And really, I'm not expecting you to read the tiny Greek letters. The point is more that basically reentrancy kind of makes that complicated because, as I've kind of already sketched, one function from your module which has access to the private memory might call some unknown function, which might be written with sort of ill intent in mind, which might call back into you, and it might call back in a sort of very twisted way. And so the interface of exactly how much it can do to your memory despite your best efforts when you're defensively programming it is a bit thorny. But while this is kind of horrible, I mean, it's a definition. You can prove things with it. You can prove it in a theorem prover. But it remains, I think, the domain of experts in a sense. I don't think a new adopter will sort of look at this and go, oh yes, this is exactly what I meant, right? But I think what we can do instead is sort of look at concrete programs and sort of see what this big definition gives us on these concrete programs. So here it's written in sort of terrible Java-like syntax that if you have a memory that you don't export and a function that has access to this memory, and where it's sort of an increment by 2 function, right? And so if it starts from 0, the memory is initialized to 0. If it increments by 2, then it should always contain, in the part of linear memory that it increments, an even value. Except that in the middle, because it increments by 2 in 2 steps of 1, you sort of temporarily break that. Now, of course, this is a silly example, but you should imagine in a bigger program that you have your module that has access to some sort of precious resource, and it can internally do potentially dangerous things, but from the outside, this should never be achievable, right? So that no evil, malicious module that you instantiate with can sort of lead you into a bad state. And then we have this function g, which is also from this module with access to this precious private memory, that calls into this unknown function that might itself call f. And so g calls h, which indirectly has access to the memory through f. And what we need is some way to state and to show that f is safe to call, even with arbitrary code in h. And this is sort of the umbrella term for this is robust safety, this term from the model checking community, this idea that you're not just safe on your own, you're safe when you're combined with potentially malicious environment or rest of the program.
Is that the same that some other communities call representation independence? Or?
I think it's linked. It's not necessarily exactly the same. I think it's robust safety has this idea that you also have a sort of functional spec. It's not just about the sort of representation. But it's very much linked. I don't think there's a clear boundary in between the two. And sort of a high-level sketch, the idea is if the 0th entry is of the linear memory is the one that contains the integer that we increment by 2, then before and after each function call to that module, this is even, but maybe not during, right? F breaks it temporarily. And then G, when we want to make sure that G is robustly safe, what we need to do is make sure that whatever the call to H, this evil function, does, is not going to change this memory here. And to do that, what we can do is leverage this idea of ownership as used in separation logic, and to say, well, when reasoning about the call to H, the evil function in G, we have to, like the logic forces us, to give H ownership of everything that it has access to or it could get access to sort of transitively. And then with a suitably defined logic, as I flashed a few slides ago, then we can show that this does not include the private memory, and so we know that, in a sense, it is safe. And Maxime's talk later will talk about that in more detail. And so to conclude, safety has many aspects, and some of them are clearer than others, and I think we would benefit from clarifying what these are, although it won't, as I've sketched, always be so straightforward to do so, and really sort of bake them into the standard so that, as universal contracts, so that users and adopters know what they get from the language, rather than as an emergent property, but really as an upfront guarantee. And I think for all of this research, there's really sort of a deep link between what people care about when they use the language, which is a bit obscure to me as an academic, and also this relatively complicated verification-linked techniques. And I think we need to talk, both me and all of you that know these things, and as a community about how we can improve WebAssembly like that. That's it.
Thanks so much. A few questions and then lunch.
Woo.
Yeah, I mean, I agree with almost everything you said, obviously. I have two comments. One is with respect to what you called external isolation. So the spec actually has in one of these appendices the embedder interface, right? Which I guess we could take a bit more seriously, maybe even formalize in some way, and then it would specify some of the things you can do and can't do. So it would rule out the weird example you mentioned before, right? Because that's not something you can do through that interface. That would be one thing. The other thing is more like a question. So you said that stack switching violates well-bracketed call returns. I don't quite see why that would be the case. I mean, it's still structured, right?
Well,
you can't return from a function that you call transitively. You still have to return from the outer function last. I don't think stack switching can change that.
Well, yes, but sort of the naive property that you really have this stack of F, G, G, F.
Yeah.
This kind of breaks because you can sort of jump up and down through things. Like the sort of the obvious notion. Like, I mean, clearly there's a property that WebAssembly 1 has that WebAssembly with stack switching doesn't have anymore, and sort of the extremely naive control flow doesn't happen. Is not guaranteed anymore.
Yeah, I guess it depends on how you model it, right? Because we have different stacks, so like you can only.
Yeah, but already you're saying, but if we have different stacks, right? And suddenly you need to change your model, your mental model.
If you view these as coroutines, then you can't then they are not nested calls anymore, really.
Yes, but then that's exactly my point, right? You need a more complicated mental model.
Sure, but I would still maintain that exact property, at least as stated, is still preserved.
But I guess it depends how you state it.
The very bare minimum you need to do is have some concept of a suspension is analogous to returning from a call with respect to the bracketing, right?
Right, which it is not, right?
You see, this is why we need to clarify these
I'm
things.
surprised you're not just agreeing with me and saying yes.
No, I mean, that's suspending, you're not returning.
Yeah,
You still, like, once you return, you still have to do that with the inner function still has to return before the outer function. There's still no way around that. You can suspend, but you cannot return before the outer function, after the outer.
Yes, but you can return from the other function without having returned. You can return from the outer function without having returned from the inner function in a way that is maybe surprising if you have a very simple mental model.
Not in the way I would define inner function. You can only do that if the inner function is in a coroutine, but not if it's in the same. Right? Okay, maybe this is too far.
Oh, your point is you're viewing the handler as like a barrier, and that's the point at which you start caring about well-bracketed calls.
It's a separate computation. You're
Yeah,
suspending one and working on another, and your inner call is a completely
Then the bare minimum is you have to start modeling handlers this way.
Yeah, sure.
Yeah, okay.
Anyway, sorry.
No, I think this is an excellent point of why we need to clarify these things, because even experts have like different mental models and don't necessarily speak the same language.
Okay, one last question, then we'll break them. Go ahead.
Yeah, I just wanted to, Burak again from Google. So in the context of memory safety discussions, like I cringed also a little bit when I saw the like safety can mean so many things, because I often like talk to the security guys who, by the way, mention all these things and they're super valuable and one should sort of be enabled to talk formally about them. But then I go and I dig out this very old thing that these ML standard, which I also like admire, you know, and also like, you know, the very basic property that in academia languages have and that outside languages don't have is the absence of undefined behavior, the absence of untrapped errors, right? You don't want the program to continue execution without knowing what happens. And we don't live in this world, right? Like in academia, we understand the value of that, but despite decades, right, like people are still using C and C++. So there's at least one sort of handbook article by Luca Cardelli that defines safety. It's a technical definition, right? It says safety equals absence of untrapped errors. Now, I agree it's a technical definition. So you can, of course, take other definitions, and maybe not the most universal, but that's definitely the definition that I can find in the WASM spec, and that, you know, and that's a valuable thing. That doesn't mean that the other things are not also valuable, especially the thing that Andreas called representation independence. I've seen in the semantic type soundness paper that has been called data abstraction, which, what does it have to do with data abstraction? Well, it means what they really mean is isolated stuff stays isolated, and they also use iris to formalize it. So that would be very valuable. But, you know, can we find a way to advocate for this without you know, giving up on that notion, that very simple notion of sort of language safety, meaning absence of untrapped errors? Because absence of untrapped errors does remain, it's not, like outside of academia, it's not the standard yet. And people don't understand it either, because the C++ spec means undefined behavior means my compiler can optimize, right? So that, like, is there a better way to talk about these things without, you know, that would be my question.
So I think that the sort of absence of untrapped errors is just one tiny corner. It's very good that WebAssembly has it. I don't know whether it's stated ever.
Well,
I guess it's a consequence of type soundness.
Probably of type soundness. There's no undefined behavior, right? Otherwise it would be type soundness.
But this doesn't include things like, for example, if you have the example I gave of if you have a module and you don't export it, then other people can't touch it.
Yes.
Right? This is completely fine. You know, it doesn't lead to untrapped error.
It's what some people call memory safety, right? So maybe
Yeah.
we need to be better around our qualifiers on the word safety.
No,
Yeah.
So, like, there's a distinction between syntactic type soundness and semantic type soundness, right? And this is like what some call semantic type soundness. That goes beyond just the syntactic. Okay, you don't have undefined behavior. You also have certain semantic guarantees beyond that. But yeah.
Maybe that's the way out, because I mean the same security folks that talk about memory safety, they never come up with super clean, crisp formal definitions. There's like, there is no use after free, etc. Right? So if you're looking for precise things, then maybe semantic type soundness is the way to.
And I would argue that WebAssembly is memory safe with respect to its own memory. Right? That doesn't mean that anything you compile into that has its own more fine-grained memory model. It's
Yeah,
going
no.
to be safe with respect to that model, but that is a different layer, and that's also actually often leading to confusion.
Yeah, that was what the Everything Old is New Again paper was talking about, largely.
And essentially also what I mean is formalizing, right?
Yeah. Well,
But isolation definitely very valuable.
Let's continue this discussion offline. Thank you. We go on last time.